Okay, here are the solutions to the section 2.9 activity on linearization. So in this first problem, we want to use tangent lines to approximate a couple of numbers. The first is 2.99 to the fifth power, sorry. So how we want to attack this is we want to find a function that we can use to approximate and a value where we can easily evaluate that function, a value near 2.99. And so what we're going to use here is the function f of x is x to the fifth because of the fifth power here. And we're going to find the tangent line to that function at x equals 3. That's a value very close to 2.99 that we can handle. So our point for the tangent line is 3 to the fifth, or 3 comma 243. The derivative is 5x to the fourth, so f prime of 3 is 405. So our tangent line to x to the fifth at x equals 3 is y minus 243 is equal to 405 times x minus 3. Bring the 243 over, and then we get an approximation for our function x to the fifth. Here it is. It's approximated by that tangent line for values that are close to 3. Well, the value we're interested in, 2.99, is certainly close to 3. So 2.99 to the fifth is approximately 405 times 2.99 minus 3 plus 243, and that is 238.95. So we can get an approximation for 2.99 to the fifth using the tangent line to x to the fifth at x equals 3. Okay, down here we want to do something similar to approximate the fifth root of 32 and 1/1000th. And here we're going to approximate x to the 1/5, because that's the function that we see here, and we're going to approximate that near 32. So let's see, we're going to need f of 32, which is 32 to the 1/5, or the fifth root of 32, which is 2. So we have our point then. The point on our tangent line is 32, 2. And to find the slope, we're going to need the derivative, and that is 1/5 x to the negative 4/5. Okay, we need to find f prime of 32, which is 1/5 times 32 to the negative 4/5. And now we need to remember how to evaluate that. That's 1/5 times 32 to the 1/5 raised to the negative 4th. 32 to the 1/5 is 2. So this is 1/5 times 2 to the negative 4th. 2 to the negative 4th is 1 over 2 to the 4th. So 1/5 times 1 over 2 to the 4th. 2 to the 4th is 16. 16 times 5 is 50 plus 30. So this is 1/80th. Okay, and so now we can write down our tangent line. It looks like y minus 2 is equal to 1/80th times x minus 32. And that tells us that our function, x to the 1/5, is approximated by 1/80th times x minus 32 plus 2 for x near 32. Okay, so the x we're interested in near 32 is 32 and 1/1000th. So 32.001, the fifth root of that, or to the 1/5 power, is approximated by 1/80th of 32.001 minus 32 plus 2. So that is approximately 1/80th times 1/1000th plus 2. So this is approximately 2 and 1 over 80,000. So there's an approximation for the fifth root of 32.001 using the tangent, not 32.001, sorry, to the 1/5 power, using the tangent line to x to the 1/5 at x equals 32, and evaluating that tangent line at 32.001 as a reasonable and really good to multiple decimal places here approximation of that fifth root. Okay. The other idea we saw in the introduction to this chapter was the idea of differentials. So the next problem puts that into practice. So the edge of a cube was measured to be 20 centimeters with a possible error of 0.05 centimeters. Use differentials to estimate the following. The maximum error in the calculated surface area of the cube. Okay, if we let x be the side of the cube in centimeters, so x is 20 centimeters. The possible error in measurement is 0.05 centimeters, so that's a small change in x. And we want to find the maximum calculated error, surface area error. And we'll call surface area S here. The surface area as a function of the side length. Well, there's 6 sides, they all have area x squared, so it's 6x squared. So the derivative of surface area with respect to x is equal to 12x. So ds is 12x dx. And we've been asked to do this when x is 20 and dx is 0.05. And the maximum error in the calculated surface area of the cube is 12 centimeters. Okay, we want to do something similar for volume. The maximum error in the calculated volume of the cube. Well, so again, x is 20 centimeters, dx is 0.05 centimeters, or 5/100ths or 1/20th of a centimeter, and now we want to find dv. So dv dx is 3x squared. So dv is 3x squared dx, and so dv is 3 times 20 squared times 1/20th. Aha, so 20 squared times 1/20th is just 20, right? So we're left with 3 times 20, or 60, and this would be surface area up here, sorry, let me fix this, is centimeters squared, and volume down here is in centimeters cubed. So the maximum error in the calculated volume of this cube would be 60 centimeters cubed. All right, there's the 2.9 activity solutions. See if you can press on to the problems that are assigned in the textbook.